Hi, my name is Colin McCaffrey and I'm going to tell you something about condition monitoring in petrochemical valves. So in the petrochemical industry, we're pumping at high pressures very flammable fluids. If we get a rupture in one of these valves, we're expelling gaseous flammable liquid to the air, one spark, and everybody has a very bad day. So at VTT, we have developed a system to monitor these valves to detect microfractures, which are indicative of the potential of catastrophic fractures. However, these occur much smaller scales and at much sooner times. So we can, in advance, determine the condition of the valve, if it needs maintenance, and if it's a safety problem. So we've designed in VTT an acoustic emission sensor. Looks a little bit like this. It's on a silicon on insulator process. Basically, this is just a capacitor where one of the planes is free to move. We've done a study of the acoustic, the turbulence, which is created by microfractures. And at the pressures we're pumping, it's approximately 110 kilohertz. So we've scaled this acoustic emission sensor to 110 kilohertz resonance. We put it in a close acoustic contact with the valve so that the turbulent flow at the microfracture can be detected using our acoustic emission sensor. The core technology here also is our patented low-power wake-up radio. So in this kind of application, deterioration of valves, it's occurring in the order of weeks, months, not minutes or seconds. So we want to measure at very long intervals. In that case, the sleeping consumption of our sensor is the overwhelmingly dominant factor to the power consumption. So we have developed a low-power wake-up radio technology, which is based only on a diode envelope detector and a low-power wake-up IC. So this consumes 6.8 microamps in a listening mode. So to integrate our system to the valves, we have taken our sensor, our acoustic emission sensor. We have glued it on the inside of a very standard bolt fixture. We've designed our readout circuit, our wake-up radio, and in this case a battery supply, which all goes inside the bolt fixture and in the end looks like this. So this is very easily integrated into our valve junctions, as you can see in this small picture here. And of course, we need also a readout circuit. So in the end application, we have integrated a very miniaturized base station to our valve device. However, here at a live demo, we of course don't bring large valves all the way. So we have also a simple USB base station device. So the live demo I'm going to show here is a little bit different to the end application. In the end application, we have only an RMS change in the detected acoustic emission signal. This isn't very interesting for a live demo. So in this case, I'm going to, with my USB base station, asynchronously wake up my sensor device. Then I'm going to apply a disturbance. I'm just going to give it a knock, and we should hopefully see the disturbance here on our very simple XL-based readout. So let me go right ahead. I'll just explain what's going to happen here. So the first thing that will happen is the base station will wake up the sensor node. The sensor will acknowledge, we'll see one little blink from the LED, acknowledge that it's awake and it's ready to measure. So after some initiation, a measurement cycle will begin, and to tell me, the diode will illuminate, and I can introduce a disturbance at this time. So then, through the active radio, the measured acoustic signal will be sent to our base station and displayed here on our XL. Right now, at the moment, we're just looking at the noise floor of the acoustic emission sensor. So now it's awake. I'm waiting for the measurement to begin. There we go. Hopefully, we will see now a spike. Yes, we do. So at the point when I introduced the step response, the knock, we see an increase in the acoustic emission, which is decaying very exponentially, very slowly. So that was the VTT and Metso automation acoustic emission sensor for valve leakage microfracture detection.